Now we are discussing a chapter, its name is Waves. The title of this chapter is Wave. What is the meaning of a wave? Before going to discuss its detailed analysis, the definition of wave we can say like this. In childhood we have played many games. So the one of the famous game is throwing the stones into a calm or steady pond or river. Let us suppose the water, we have different locations of water, different resources of water. It was steady, calm. So it may be a river or ponds. Suddenly we have dropped a stone at one point. Where we have dropped the stone is nothing but the origin of the wave. And in our general words we used to say this was as point of disturbance. This disturbance was uniformly distributed over a volume on the surface of water in a circular wave. Like this, uniformly distributed. That means whenever the disturbance was created at one point in a steady river or steady pond, and this disturbance is distributed over the entire volume of the surface of the water through up to some limited range, then we can say that the carrying the disturbance along with the energy or the transfer of energy towards the different points from a common position is called wave. So a wave can carry the information in a form of energy. Carrying the information towards long distances or carrying the energy towards long distances is called a wave. We are not discussing the propagation of the waves and parameters related to the wave. We are just defining a common nature of the wave. So it carries the information, it carries the disturbance towards the longer regions, and it carries some energy also. The stone which was dropped, it is creating the force, a disturbed force converts to energy and passing over a volume. And when we see a cork, a rubber cork which is made up of a rubber material, while it is oscillating on the float of water like this. Suppose this is a rubber cork. When it is oscillating, it is tilting like this, means moves up and down. Some part will be down, some part will be up like this. When it is doing this up and down oscillatory motion, this disturbance also can be created at that point of up and down, and it will be distributed over the entire volume. Here also we can say that the disturbance was carried to the longer distances. So this is the general view of the wave. These waves are two types. One is mechanical wave, second one is electromagnetic wave. So in this lesson, we used to discuss about the mechanical wave. So before going to discussion of the mechanical wave, we should discuss about the classification of the waves on the basis of propagation. Now we will see the classification of waves, nothing but the types of waves. So we can say that wave is the transfer of energy from one point to another point. So wave is defined as the transfer of energy from one point to another point. These waves are of two types. One is mechanical wave. Mechanical. What is the meaning of mechanical? In case of Newton's laws, we have discussed about mechanical force. Means if a force was applied by a human being to move an object, to change the shape of an object, to change the direction of an object, these all forces are under the mechanical forces. So the mechanical wave means the waves which were produced by machines, the waves which were produced by the human beings, the waves, best example a sound wave, these all under the mechanical waves. These mechanical waves are defined like this. If a wave requires a material medium to propagate from one point to another point, those waves are called as mechanical waves. So if a wave requires a material medium to propagate from one point to another point, those are called mechanical waves. So what we can see the examples in this case. Suppose this is the board. Suppose I am applying some force on the board. So simply a sound is coming out of this. Means I am applying my mechanical force at one point on the board, and the disturbance was created in this board, in this solid body, and this disturbance is coming out in a form of sound energy or sound wave. So if I am pushing a body, pulling a body, I am throwing a ball, these all are the mechanical expressions of the wave. So what we can understand is the mechanical waves requires a material medium. What are the material medium we have to propagate? Air is the medium, liquids are the medium, solids are the medium. So this is the materials we have to propagate the sound. That means these waves need a medium, are dependent on medium to propagate. The best examples are sound waves, the crest and trough. We can observe the tidal waves in the ocean, tidal waves. So these all may be a sound wave which is created through a mechanical rod or a machinery rod, the bus horn, train horns, these all are the mechanical waves. So we can say many big list of these examples. So the maximum velocity of these mechanical waves in air is 340 meters per second. Such like this, we can experience the mechanical waves in our daily life. The next classification in the category is transverse waves. So the next classification in the types of waves is transverse wave. This transverse wave is also called as electromagnetic wave. So what is the electromagnetic wave? In the previous case, we used to compare this one in transverse wave, but we can say that electromagnetic waves are such type of transverse wave. But all transverse waves are not electromagnetic waves. There are many sound waves which are transverse in nature. So it is a type of transverse wave in the subclassification of the waves. So electromagnetic waves means these waves doesn't require any medium to propagate, and they can travel through vacuum also. So if the waves are not required of a material medium and can pass through the vacuum are called electromagnetic waves. So these electromagnetic waves doesn't require any medium to propagate. They can travel through vacuum also. What are the best examples of these electromagnetic waves? Light rays, X-rays, gamma rays, beta rays, alpha rays, all the radiations that are ejected from the black bodies or the radioactive bodies, and infrared rays. These all are under the examples of electromagnetic waves. Most of this electromagnetic radiation contains in the sunlight only. So sunlight is classified into two types. One is visible light and another one is invisible light. So the invisible light to the visible light we can classify as electromagnetic spectrum. So in this case what we can understand is these all rays that can travel with the speed of light, that is nothing but 3 into 10 to the power of 8 meters per second, which is very high when compared to any other waves or any other energy sources. So they can travel through vacuum. Best example, sunlight, the distance from sun to earth is approximately 1.5 into 10 to the power of 11 meters. Still 2/3 of it is filled with vacuum. Still we are experiencing the sunlight on the earth. This way we can prove that the sunlight are the electromagnetic waves that can travel through vacuum also. Now we should clearly discuss about the mechanical waves and their propagation and the characteristics that are associated with the mechanical wave propagation. Now we will discuss about the mechanical waves. These mechanical waves are defined as it is such a transfer of energy from one point to the another point that is produced by the repeated periodic motion of the particles of the medium about their mean position. So this is called a mechanical wave. If you want to produce the mechanical wave, we should need a medium. This medium is called elastic medium. Otherwise, the particles of the medium doesn't propagate or doesn't repeat the oscillatory motion. So it is a type of transfer of energy from one point to another point due to the repeated motion of particles of the medium about their mean position. To produce these type of waves, we need an elastic medium. So what are the characteristics of the elastic medium? Yes, they have the compressibility, they have the property of expansion also, so we can say the expansion and compression is in the regular orders of intervals or alternative order. So these are the characteristics of the elastic medium. So elastic in nature, if a medium possesses these type of characteristics, we can say that one as elastic medium. So what are the examples of the mechanical waves at different parts we can observe? The first one is waves on water surface. Second one is waves on ropes or strings. Now we will discuss these two examples under the case of mechanical waves with examples. So one of the example in the mechanical waves is waves on water surface. So the waves on water surface means, as we discussed previously, so this is the water surface. If it is the dimensions of the water, maybe it is a river or pond. Water is located like this. Whenever a point of disturbance due to a stone, due to any object was created at any point of these dimensions of the river or pond, then it creates a circular loop around it up to some dimensions. Actually, it is appeared to be circular loops, but if you see, it is a continuous propagation of compression and rarefaction, or expansion or compression. So it is like this. So we can see the water wave propagating like that. So as it is going to decrease, as it is going to further, its amplitude is going to decrease and continuously like this. So this is the point of disturbance. On either ends, we can see the same propagation like this. So the intensity increasing and suddenly decreasing, again increasing, decreasing, again increasing, decreasing. So like this, we can say that it is the elastic behavior of the medium, which goes to the expansion as well as compression, repeatedly maintaining the regular time intervals. This is called elastic behavior of the medium. So when the point of disturbance is occurred, water behaves as an elastic medium, then we can observe these wave propagations on either ends. It seems to be the locus of all these wave propagations are seen to be circular loops around a common point. But we can see the crests and troughs or tidal waves like a tidal shape on the water surface. Same thing will happen on the ropes also. If it is a rope or thread, what we can understand from this rope or thread, suppose if a rope is connected at one end and free at another end. Suppose if you disturb this free end, then the wave propagation will be like this. Like this. And this crest which was formed at the point of disturbance, it will keep on moving along the length of the rope. So for the next one, this one will create like this. For the next level, it will be like this. Next, it will be like this. And automatically, it comes to rest. See, this crest which was formed at the point of disturbance is continuously moving towards the fixed end of the rope. So the force at one end and force at this end, these two creates the loop. So this is also a mechanical wave. It is also the elastic nature of the medium, which can expand and which can compress at regular time intervals by means of its mean position. This is also called a wave motion in the ropes or thread. Now we will discuss the different types of waves and their propagation with respect to its characteristics. Now we will discuss the different types of mechanical waves. These mechanical waves are again classified into two types. One is longitudinal wave. Yeah, in the title itself, it is a longitudinal, means lengthy. So what is this longitudinal waves? The particles of the medium moving back and forth along the propagation of the wave is called a longitudinal wave. That means in longitudinal waves, the particles of the medium moving back and forth about their mean position along the propagation of waves is called longitudinal. What are the examples of these longitudinal waves? Sound waves created in metal rods, and motion of the particles in an air column in an open tube, one end open tube. So the motion of the particles in an air column, the to and fro motion of the spring, these all are called as or subtitled as examples of longitudinal waves. And what is the characteristics of these longitudinal waves and how the air particles will behave in such cases we will discuss now. So this longitudinal wave mainly consists of two parts: compression, rarefaction. And rarefaction. So what we can understand from this compression or rarefaction? Let us try to assume a tuning fork which is of the Y shape. Like this. When I have beaten this tuning fork at one end, it used to vibrate about their mean position like this, away from the mean position and towards the mean position. So the air particles or the particles of the medium are moving away from the mean position or towards the mean position. These are the two cases. If suppose all the particles of the medium are moving away from their mean position, means the particles of the medium are moving away, means volume increases, density decreases. The volume of the air column increases, all are moving away. So that's why if volume increases, density decreases. So what we can say that if these all are moving away within a given over volume, So this is said to be a rarefaction. But what about the compression? When all the particles of the medium is propagating towards the mean position of the disturbance, then volume will be decreased and the particles will be surrounded closely like this. So more particles of the medium are crowded within a small given volume. That means its density is going to increase. That's why it is better to draw very close to close. So here to here, what is the difference? Here, more particles are crowded in the given volume. That means density increases, volume decreases, correspondingly density increases. Suppose if this is the given volume, we can approximately see some 10 to 12 particles in this volume. But here, more than 20 particles are there. Density increases because density is mass by volume, inversely proportional to the volume. Volume increases, density decreases, and vice versa. So this part is called compression. So what is the meaning of this? Rarefaction, expansion, similar to the expansion. So in case of expansion, volume increases, density decreases. But in case of compression, all the particles are moving towards the mean position. So more crowdness or crowded particles are more within a given volume of the interior. So this is called compression. The center of the two successive compressions or the center of the two successive rarefactions is called wavelength. So lambda is equal to the distance between the centers of two successive compressions or rarefactions is called wavelength. That means this is the compression, and again we will see and more rarefaction, then again compression. So we can observe the more crowded particles within the given volume like this. So we can immerse more points to fill the gaps. So this is compression. This is also compression. So this is rarefaction, this is rarefaction. So from centers of rarefaction to rarefaction is called lambda, or the centers of compression to compression is called lambda. Like this, we can represent the wavelength in terms of compression and rarefactions in case of longitudinal mechanical waves. The next subtype of the mechanical wave is transverse wave. What is this transverse wave? It is collectively called as a transferred and reversed wave at the same time. So how it is defined with the examples we will see now. So in case of transverse waves, the particles of medium are vibrating up and down about the propagation of the mean position. That means if the wave is propagating like this, which is via passing through the medium. So the particles of the medium moving up and down right angles to the propagation of the wave. So up and down, up and again down like this. Or we can extend this line also. So the particles of medium or of the medium vibrating up and down and that to be right angles to the propagation of wave. Is called a transverse wave. So what we can understand is, yes, the particles once it moving up and coming down, moving up, coming down. So it is an oscillatory motion about the mean position, that to be in right angles to the propagation of the wave motion. So when the particles are moving up, it creates a lot of density at one direction. So this is called crest. So this is called crest. What about the down peaks? Trough. TROUGH. So the distance between the centers of the two successive crests or two successive troughs is called wavelength. The distance between the centers of the two successive crests or troughs is called the wavelength. That means the wavelength of a transverse wave. Symbol is lambda. So graphically we can represent like this, or like this, where we can produce these transverse waves. Suppose if a string is fixed at two ends, if you try to disturb the string at any point perpendicular to each other, perpendicular to its length, then it will vibrate. We can observe the wave propagation like this. So first the waves will transfer to one end. There these ends are acted as the obstacles for the wave propagation, that's why they will be reversed back. So the incident wave in this direction and the reversed wave will meet at right angles to the propagation of the string in a form of loop, and this creates a transverse wave. This is a small demonstration of the formation of transverse waves. What are the examples of these transverse waves? The sound waves which are produced in the musical instruments, the ripple on the water surface, the waves which are produced in the strings which are fixed at two ends, or the waves which are connected at one end and second end is free. If the vibration was started at the free end, when it is propagated to the connected end, that is also called as a transverse wave. So what are the examples? The examples for these electromagnetic waves in other way, all electromagnetic waves, especially propagation of light, propagation of X-rays, propagation of infrared rays, these all are radio waves. These all are the example of transverse waves. So the example of transverse wave, naturally we can say that electromagnetic waves. So like this we can define the transverse wave as well as longitudinal waves. Now we will discuss a few differences between these two waves. So now we should discuss about the differences between the longitudinal waves and transverse waves. So it will be a table like this, a longitudinal wave, on the another column transverse wave. So the first difference in the longitudinal wave and transverse wave is, it is nothing but the propagation of the particles of the medium. In longitudinal waves, the propagation of the particle medium are along the length. That means the particles of medium propagates to and fro about the mean position. Or we can say along the length. But in case of transverse waves, if you see, the particles of the medium are right angles to the propagation of wave, that to be up and down. The particles of the medium propagates up and down and right angles to the propagation of wave. This is one difference between longitudinal and transverse. The second difference is, longitudinal waves creates the alternative compressions and rarefactions. It can create the compression and rarefactions. But in case of transverse waves, it is creating the crest and trough, upward and downward manner. This is the crest center of propagation. Longitudinal waves will be created in any type of media, whether it is a solid, liquid or gas. It can be produced in all type of media. Like solids, liquids and gases, etc. But the transverse waves, they are produced only in solids. In longitudinal waves, according to the propagation of the wave particles, there is a large variation in the pressure. So, pressure difference will exist in the longitudinal waves. But in case of transverse wave, there is no chance for the pressure variation. Pressure is constant throughout the propagatory motion. So, like this, we can see the differences between or distinguish the longitudinal wave and transverse waves. Now we will discuss the wave terminology. Means the propagation of wave is associated with many parameters. So we will discuss one by one. The first one is amplitude of the wave. Suppose if we observed a transverse wave or longitudinal wave, let us suppose for our easiness we are discussing a transverse wave. Whether it is the propagation of the wave, the arrow mark shows the mean position of the wave propagation. So it will be away from it or towards it. The maximum displacement in tangential direction from the mean position of the wave is called its amplitude. So the maximum displacement of the particles of the medium in tangential direction from mean position is called its amplitude. Its symbol is A. So it is a to and fro motion in case of longitudinal waves also. That means we can represent the motion of the sound waves or longitudinal wave in SHM equation also. Let us suppose if it is y is equal to a sine kx minus omega t, like this. This is the wave equation of the longitudinal or transverse. This A is called amplitude. So it is the maximum displacement in vertical direction. That means if 2 or 3 waves are represented like this, and one more wave is like this. So whose amplitude is more and which wave will travel to the longer distance within the given same time interval is the second wave, because its vertical displacement is more than the first one. So amplitude is more means its displacement is more and the sound wave can travel to the longer distances as rich as possible in the given time interval in the comparison. The next terminology of the wave is wavelength. So what is this wavelength? So it is the distance traveled by a wave in a given time, where the particles of the wave or medium completes one cycle or one complete vibration is called wavelength. That means it is the distance traveled by a wave in any given time where the particles of the medium or wave or of the wave completes one cycle or one vibration. So how can we understand this wavelength as graphically? Let us suppose this point is the origin of the wave propagation. If you see the crest and trough of the wave, this is one like this, and if you can extend to one more down peak also. If this is the wave propagation, if you see the definition, particles of the wave should complete one cycle or one complete vibration. One cycle means it is suppose the top peak, down peak. So this up peak is the propagation in forward direction. The down peak is the propagation in the downward direction in the negative scale. So almost every point, the starting point of propagation is 0. So it is pi, it is 2 pi. We say that the two opposite poles means if it is a straight line, here it is 0. Once the particle is reaching the exact opposite side of the initial position, the angle change is 180 degrees. If two particles faced each other, the angle between them is 180 degrees, we know that. So in radians, it is represented by pi. And from it is again coming to the original position in the opposite direction, like this. If it creates a circular loop, like this, then if we draw a middle line for the equal bifurcation of the circle into two halves, so this is 0, this is 90 degrees, this is 180, and again it is 270 degrees, and again it is 360 degrees. So 0 and 360 are coincides on each other on the same scale after completing one complete cycle or one complete vibration. That's why it is from 0 to 2 pi. So what we can understand, the crest to crest is wavelength, or trough to trough is also wavelength. So in other words, we can write wavelength is equal to 2 pi also. This is said to be wavelength of the wave. The next terminology which is associated with the wave propagation is time period. What is this time period? The definition of the time period is same as mechanics. So in simple harmonic motion also we have discussed this time period. So if it is possible, the same definition we can write here. So what is the time period? The time taken, the actual time taken by a wave for its complete cycle or for its complete vibration. The actual time taken by a wave to complete one cycle or one vibration. What is this one cycle or one vibration? That means if it is the wave propagation, again we can use the example that was shown in the wavelength also. This is the point 0, half rotation, full rotation. Again coming to 2 pi in the opposite direction, like half of the circle, again full of the circle, 0, 180, again 360. For one complete rotation or one complete cycle means where the object has started its motion, again it should come to the same position after a time interval. That is said to be one complete cycle. In case of SHM, if this is the oscillator, if I am prolonging to this direction, if this is the observed point, the body should come again to this position. That means to this half, to this full. So it was moved to the opposite direction. From there in opposite direction it is reached to the original position. So we can compare this situation here also. It was traveled from 0 to 180 or pi radians. Again in the opposite path it has reached to 2 pi. This is called one complete cycle. The next one is frequency. So what is the frequency of the wave? Frequency is nothing but how frequently a body is coming to this mean position, or how frequently the body is coming to its original or mean position. So in other words, we can say that the number of vibrations or number of cycles did by a wave in one unit of time is called its frequency. The cycles are the number of vibrations covered by a wave in one unit time or in unit time. Here the unit time is called seconds, is called its frequency. So the symbol of frequency is F, it is equal to 1 by time period. So its SI unit is second inverse, it is also called hertz. So these four are the physical quantities that were associated with the wave propagation. Now we will see the relationship between all these physical quantities in the wave propagation. So the next concept is relationship between wave velocity comma frequency and time period. So we know that velocity is equal to displacement by time. If the displacement or if the propagation of the wave is in a straight line, we can write displacement is equal to distance also. But how we can define the wave velocity? Let us suppose if the wave is traveling like this. Wave velocity is defined by wavelength or the distance traveled by the wave by time taken. So wave velocity is equal to distance traveled by the wave by time taken. So the distance traveled by the wave, it is nothing but the wavelength. So it is wavelength by time taken. So the symbol of the wave velocity is V. So if you see the continuation, V is equal to, symbol of wavelength is lambda, time taken is T. This is the relationship between wave velocity and time. But 1 by time is equal to frequency. So I am substituting 1 by t is equal to frequency symbol, whether it is nu or f. Anything we can substitute. So therefore, V is equal to, we can write lambda into 1 by t. Therefore, it is nu lambda or f lambda. From this expression, we can say that V is proportional to lambda. Means velocity of the wave is directly proportional to its wavelength. That's why V by lambda is constant, and this constant we can say as frequency. So what we can infer from this expression, a velocity or wavelength may change, but they are under the proportionality limit. That means if velocity is increased by a factor, lambda also increased by the same factor. Velocity is reduced by a factor, so lambda is also reduced by a factor. In all cases, frequency of the wave is constant. So frequency is the only physical quantity in the wave motion. It is constant throughout the wave propagation.